Hi, my name is Waleed Al-Kami, and this is Lab 5, Physics 2211. As an intro, Lab 5 is supposed to be like a capstone. The purpose of my lab is to use the energy principle to measure intrinsic properties of systems. To be specific, my lab is trying to find the incline of a ramp based on the final and initial velocities. Any ramp, any curve, if you know the final and initial velocity and the distance, the model that I get out of delta E total is going to give you an approximation to what the angle of inclination of that ramp is. The fundamental principle is the energy principle, delta E total equals work external, and I'll show you how we derive our model. As just a brief summary of our main results, this lab is two parts. The first part is what is the incline. So I had the system, a bottle, and this ramp, which is about like 16 to 15 degrees. And you can see VPython glow script gave me about 14.5, which is really close. And I didn't need to use any gadgets, any tools. I just final velocity, my initial velocity was 0, so I just had the final velocity and the distance of my ramp. And using pure physics, I managed to get a fairly good approximation of my incline. Part 2 was, if I know this incline, and say I want a certain final velocity here, because I want to do some system or some whatever, what initial velocity do I need here to get my expected final velocity? Essentially, what I did was I just graphed the final velocity possibilities based on the initial velocity. So if you don't push it, which I didn't, you get about 0.8 meters per second. But then you can see if you do 1 meter per second of initial velocity, this is how much you get. And you can kind of predict the final velocity as you wish. All right, now the fundamental principle on how we got to our equations of motion. So we first of all assume that on our ramp right here, on the ramp that we saw, we're not expecting friction, right? So we're not going to solve for any frictional forces. We're going to say the work is 0. So delta E equals delta K plus delta UG. Only kinetic energy and gravity is changing. And then we solve for theta. Theta is just this equation. I added an adjustment to make my theta more accurate, and this adjustment is also used in my final velocity. And so from theta, I also get the final velocity. An interesting note to see is the final velocity of any object you roll down any ramp does not depend on the mass. It doesn't matter what the mass is. The velocity is independent of mass when it's going down the ramp, which is quite an interesting thing to think of. Now, this was my tracker. So I tracked the bottle to get kind of that final velocity around this point. And this is my code. First of all, you have your initial conditions, G, my V final that I measured, which was about 0.8 meters per second. My initial was 0, and then I measured my ramp. And this is what we're going to talk about in part 2. I also made the graph here for what you saw in part 2. So the first part of my function or my code is to find the incline. We solve for theta right here, and this gives you radians. So then I just multiply it by 180 over pi to give you the angle in degrees. That prints it out. And then I do a calculation loop for part 2, which is what is the final velocity based on the initial velocity. And I do V final equals that equation that we solved for before, while V initial is less than V initial max. So you give it a max V initial that you're going to do. And you want to say, I want to see the final velocity of my object going down this specific ramp that I solved for, with V initial being between 0 to like 5 meters. And you'll see a whole graph of possible V finals that you can accurately predict. So discussing our main results, what does it mean? What does the final velocity tell us about the ramp? Well, we saw before, the final velocity is based on what is sine theta and cosine theta. The final velocity is proportional to theta. The greater the theta is, the greater the final velocity is, right? And so that also ties into how we predict theta by V final. You can intuitively think of it as if the bottle comes down at the end very fast, you naturally think, hey, the ramp is very steep. If it comes down very slowly and reaches the end at a slow speed, you expect it to be fairly flat. That's why. That's the energy principle in real life right there. Now, what if the surface was rougher or the ramp is longer? Now, in terms of the first case, I did say we did not evaluate work, but there is some friction going on either inside the bottle or on the surface that we're not accounting for. I conveniently accounted for that using the adjustment that I showed you. But in any case, if there's more friction, the velocity will be lower when it reaches the end. And guess what? If the velocity is lower using my model that you can solve for using the energy principle, if it's lower, then you would expect theta to be smaller than it actually is. All right, so the model might not be accurate when there's significant frictional forces going on. Now, if it's longer, again, essentially what we're saying is all the gravitational potential energy is converted to kinetic energy. So the larger the gravitational energy, i.e. the longer it is, the larger the final kinetic energy is, the faster it is. Possible errors, we could have used an incorrect tracker values and got an incorrect initial velocity. And 2, the bottle has liquid, so again, there could be some funky work happening that changes our motion. To conclude, the energy principle can be applied to measure intrinsic qualities of a system, like the incline of a ramp, friction, and so on, using only motion data. You don't need tools to measure incline. You can do it using the energy principle. And thank you very much.